Od atmosféry cez oceány až po pevninu. Veda nás obklopuje na každom kroku. Vítajte pri Vedátorskom podcaste, v ktorom sa budeme rozprávať o vede a prírode okolo nás. Moje meno je Jozef.
Ja som Samuel.
Tento podcast vychádza v spolupráci so SME. Tento podcast bude v anglickom jazyku, nakoľko sa rozprávame s pánom doktorom profesorom Lawrenceom Kraussom,
ktorý nevie po slovensky,
Áno,
ale kto chce, tak to nájde na YouTube, kde si to môže pustiť titulky a budete to mať všetko v angličtine. So we should switch to English.
Yes.
That's a good idea.
Professor, doctor, how we should...
Air doctor, professor. No, just Lawrence will do.
Lawrence will do.
Okay.
Hello, Lawrence.
Hi.
Thank you very much for coming to our podcast. It's a big privilege.
It's a pleasure to be here.
How do you find Slovakia so far? Is it your first time here? Or?
It's my first time in Slovakia. Yeah, it's been, I've had a lovely whirlwind time here so far and enjoyed the old town last night walking around.
Oh, okay.
Met some fun statues.
Yeah, we have a lot of fun statues.
Yeah, but no worries, usually it isn't this cold at the beginning of September.
It's okay. I live in Canada, so it's not a big
So
surprise.
this is baby cold.
Should we blame the climate change for this weather or...
No, there's a difference between weather and climate, and people confuse them all the time. So weather happens on a day, climate happens everywhere over time.
But still climate scientists are telling extreme weather is more probable, so maybe...
But you're right. Probability is different, so you can say the probability is greater. And in fact, something, although I talked about climate here yesterday, something that is interesting that I talk about in the book that I didn't talk about is the fact that if you actually look at the weather everywhere on Earth on a given day, and then you can actually begin to see a signal for climate change. And, on a given place, obviously the variation is such that you can't really tell. But if you look at all the places and look at the average deviation from the average temperature, there you can actually see some statistically significant changes. So even weather gives a signal for climate change.
Okay, you wrote a book about climate change 4 years ago?
Probably.
During COVID.
Yeah, during COVID,
because we started our podcast during the time, and you have some references to COVID and to lockdowns and so on. How was it to write a book about climate change during biggest pandemic of our lives?
It was, the pandemic, of course, was awful, but it was a blessing if you're writing a book. I couldn't do anything else. And I think I was telling Samuel that most of my books have taken, on average, 2 years to write. That book took 10 weeks to write because I had absolutely nothing else to do, and everything else I was doing was canceled. And to tell you the truth, I was thinking about what people were doing on the front lines and trying to help people. And I thought, what can I do? And I thought, maybe this would be a useful thing to do. So that actually motivated me to write the book then.
Oh, okay. Great. And you started your book saying that why astrophysicists would write a book about climate change. Can you walk us through this process? Because I found it very fascinating, your thought process.
Well, because there's a number of reasons why I wrote the book. First of all, primarily, I wrote a book. I wanted to write a book about just the science of climate change because, at least in the United States, but I think elsewhere, there are many people who want to deny the existence of climate change, primarily because they're worried that people are going to tell them what to do. They're going to take away their cars or not, something like that, and so they don't want to hear it. And when you don't want to hear it, you tend to stop listening to anything, and you're willing to not believe the data. So if I could just write a book about the science and not tell people what to do, that maybe I might reach more people who could at least understand the science behind it, realize it was real and fundamental and well established, and then they could decide. You can look at it and decide it's not worth doing anything if that's what you if that's what you think. And so that was part of it, but also, as a non-climate scientist, the impression that I get from many people is they think that climate science is first speculative, and secondly based on detailed computer models that we can't trust. And I think that's obviously a mistake. And I suspect many of the climate scientists sort of sometimes can't tell, as we say in English, the forest for the trees, namely get so stuck in details that you don't step back. And I thought it would be if I, as a scientist, and secondly, as someone who spends a lot of time explaining things to the public. If I couldn't explain it in a way that was clear, then how could I expect anyone to understand it? So I thought it's perfectly reasonable for a reasonably educated non-climate scientist to try and talk about it. And then what became more fun is that I thought the science is fascinating and the history is fascinating. And the more I delved into it, the more I found it really kind of interesting to see the various episodes that impacted on our present understanding.
Yeah, the history was very interesting because one of the first people, I don't remember the name of the scientist that proposed the climate change, was from Norway, and he was excited about the climate change and the warming of the candidate.
Yeah, Sweden actually.
Oh, Sweden, sorry.
But, yeah, no, that's right. He was really hoping that he saw this as a great opportunity.
For Scandinavia.
For Scandinavia to get better. Yeah, he was very optimistic. He was an interesting guy, Arenas. He was the first. There again, I'll give you a little snippet because there were fascinating parts about his life. He was the first Swedish Nobel Prize winner in chemistry, which is interesting since he was the head of the Nobel Committee. But it turns out he did important things. But he throughout his life he somehow managed to eke out success out of failure. He got one of the lowest grades for his PhD exam. Yeah, and he convinced them to raise the grade. Then he got a position, even though most of the people didn't want to give him a professorship. And then he became head of the university, even though people didn't like him. And then he became head of the Nobel Institute. But he did important work.
So he was social pariah.
Yeah,
but his work was influential.
Yeah, but he wasn't really a pariah because somehow he overcame all of that and got these every good position. And interestingly enough, he used the work in his thinking about climate change was strongly based on an earlier scientist, Högberg, who was a geoscientist, who did the kind of calculations I really like. I talked about it here the other day, and it's in the book, that Högberg asked an amazing question. Often when you talk to people about climate change, they think, well, how can humans affect the climate? I mean, we're just these puny beings here. Yeah. And he asked, well, he could estimate how much carbon there was in the atmosphere, because even then there was a rough idea, knowing how much it was, and you add it all up, it's about 600 gigatons, 600 billion tons. And then he said, what happened, how thick a layer would that be if you liquefied it or turned it into a solid? And it's only 1 millimeter thick. And he said, well, let's look at the soil on Earth. Life already affects things much more than 1 millimeter. Mm-hmm. So probably life could affect the amount of carbon in the atmosphere. It was a really brilliant kind of back-of-the-envelope calculation, which I think is so important in physics.
And this is very misleading about the atmosphere. Like, it seems it's stretching all the way up. Yeah. If you liquefy, it will be 10 meters. Yeah. That's the pressure of it. So.
Yeah. And, and the other thing, actually, it was a friend of mine, actually a well-known scientist, Martin Rees, we were talking, and people say, well, how can such a small amount of carbon affect, the heat coming from the sun and everything else? Well, if you think about it, if you take a little piece of paper and put it over your head, it blocks the sun out pretty well, and it's pretty thin compared to the weight of the entire atmosphere. But somehow it can have a dramatic effect. So it's not too surprising that small things can.
And if there is a mist, you can see nothing.
Yeah,
basically,
exactly. So. Like today, sort of in a way.
Yeah. So. You said that, well, you are a cosmologist, but you can write about simple stuff about climate. But I think there is more to it, because yesterday 2 quantum gravity guys met at a stage discussing this. So I think it's not like you can write about climate, but your career made you like sensitive to important details, and you can explain them simply. So it's, when you want to write and make podcasts about the universe, you have to be good at picking the stuff that can be explained and that can put together some kind of narrative about a complex topic. So I think you are underselling yourself. It's not just about like you can write about the simple stuff, but you're good at picking the important points. And
well, the more you do it, I think the more experience you have learning what works and what doesn't work. But thank you. Yeah, obviously I spend a fair amount of time on it, and And you know, I don't know if you've had this experience. I've written a dozen books, and I often forget what I put in them, and and sometimes I have to admit I read it and go, "Hey, that's not too bad."
This guy is smart.
Yeah. So you said that you try to not to touch some sensitive points because people get very polarized. And this topic, same as during the pandemic, the topic got very polarizing as well. But do you think, is this like a sign of stubbornness, or we have failing education, so people are not capable of grasping those complex topics? Or
I think it's all of that. I think people are stubborn. People want to believe, first of all. Everyone wants to believe what they want to believe. So we have to understand that. And scientists are the same way. And the whole point is that science overcomes the stubbornness of scientists when they're wrong. The scientific process overcomes the natural tendency of scientists to want to believe things that they like rather than the way they really are. But I think we also are doing a disservice in the way we educate people about things. And it's not. I think it's important to realize that I avoided subjects that I didn't think were relevant to understand the science. But I don't believe one should steer away from sensitive topics if they're relevant. And I think that's really important. But, you know, we don't expect people, when it comes to scientific issues, we don't expect people to think. And that's really surprising me because, you know, if you have a history book or an economics book or a social science book, you expect people to work through complicated arguments in order to say. But when it comes to science, we give up expecting people to even see an equation and somehow be able to understand what it means. And people are actually capable of doing it, but they convince themselves they're not. And I think we do people a disservice by catering to that willingness to not have any quantitative thinking about things. And you see it a lot in simple things. If you just estimate things, you can guess whether you're right or wrong. And, you know, I remember, maybe this has happened to you, but you go to the grocery store and there's a cashier and they make a mistake, you know, and you have 3 items and they go, "Oh, it's $3,000. You know, hold on a second. But that's what the machine says.
Only 2,000.
Yeah. And, you know, and you say that, you know, they say that's what the machine says. So it's really useful to have these tools. And, you know, I wrote a book called Fear of Physics once, and it was about the tools that we use to try and understand the world. Because science is all about taking a very complicated world and in some sense simplifying it enough so we can extract out the important details. Because, you know, just understanding any given thing, how a piece of paper falls, is so complicated that if you didn't, as Galileo did, avoid the idea of air and all of that, you wouldn't be able to extract out the important principles that ultimately reveal the way the universe works.
And regarding the difficulties, when you are, I don't know, writing about the universe, I think there is a natural ladder. You are increasingly discovering more difficult stuff. With climate, it's like simple equations, and then very quickly it's like supercomputer simulation. Yesterday, during your presentation, it was very quickly from Stefan Boltzmann law to supercomputer simulations about how to bridge this gap in complexity.
I think it's interesting you think it was very quickly. I suspect if you asked the audience, they wouldn't think that because the simple stuff was complicated for them. That was, you know, when I put a simple equation, I could just see the horror on people's faces when I was talking. And again, but the essential idea, I showed sort of heuristically the effect of carbon changes, how it changes the absorption of the atmosphere. And then I showed a supercomputer calculation that mimicked it. And I think the important thing is to say that it's not as if the supercomputer calculations demonstrate any new fundamental physical processes. They just allow us to understand the details. And climate, and the details of climate are complicated. The overall picture of the effect on the Earth and its overall change in temperature is not particularly complicated. But, you know, there's lots of effects. There's currents, there's winds, there's all sorts of things. There's clouds, there's all sorts of things that when you add the details one by one make it much more complicated. But that's true of life in general. And the idea is often, the important thing is to know what to throw out and what not to throw out. And that's almost an art. in science. But generally, I think I started my book, Fear of Physics, with a famous joke, at least among the physics community, which, and I'm sure you've heard it in different contexts, but the joke goes that a psychologist, an engineer, and a physicist were called into a dairy farm because the farm wanted to produce more. And they each were given a week to explore and analyze the things. And the psychologist comes back and says, well, you should paint the barn green because the cows will be happier and they'll give more milk. And the engineer says, well, I've checked the size of the milking tubes and they're a little too small. They should be bigger so the milk can flow more carefully. And the physicist comes out and first asks for a blackboard, of course, and gets a blackboard and then draws a circle and says, assume the cow is a sphere. Anyway, yeah. Okay.
Sphere in a vacuum.
Yeah.
And maybe one last thing about the climate change. Yesterday you mentioned geoengineering, and you got many people ask us to make an episode about this. So what is your stance on this?
Well, my views have changed somewhat. By the way, I think it's inevitable. I think it'll happen, whether we like it or not. Because I think
you mean here on Earth?
Yeah, here on Earth. Yeah. I don't think it's going to happen on Mars, no matter what. Well, not in the foreseeable future, no matter what Elon Musk might want to do. And I don't even think he'll get to Mars, but that's a different thing. But the point is that I suspect that political systems will hamper the response to climate change, and there may be some climate emergencies. And because, as I pointed out yesterday, geoengineering has the virtue and also the danger that, unlike trying to reduce carbon output, which requires cooperation of all the countries in the world, basically, if you want to put aerosols in the atmosphere, any one country, any one business, for that matter, could do it, and that means that you don't need to have the whole world agree to something. But it also means, so that's the danger. Any one country could decide to do it, but also it's the virtue because it means it can be done. I used to be opposed to geoengineering because we don't know what's going to happen when you put aerosols in. We know, yes, you'll block some sunlight, but what other things will happen? And one of the things that I did mention would happen that I hadn't realized, I learned from Elizabeth Kolbert's, who she's a great science writer. Her book Under a White Sky is that if you tend to put aerosols in the atmosphere, the sky color will change from blue to white, and so children in the future won't be looking at a blue sky; they'll be looking at a white sky, which seems kind of sad and unromantic. But I'm not as opposed to geoengineering as I was, because again, one of my geoscience colleagues pointed out to me that unlike carbon, which more or less stays in the atmosphere for almost 1,000 years, aerosols put in the atmosphere dissipate within a year or so. So even if there are negative features, they won't last 1,000 years.
You can turn it off quickly.
You can turn it off relatively quickly. And so it's the kind of experiment that doesn't seem horrendous. So I'm not as opposed to the idea of geoengineering as I was before. And you can also do experiments, and some people are doing experiments, simple experiments with aerosols to see what the impact is. And the other negative that people point out, and it is somewhat true, is it's not a cure. It's a Band-Aid. Mm-hmm. And so it allows you to take more time to do what really needs to be done. And some people say, well, if you have geoengineering, then there'll be no motivation to try and
exactly. That's and exactly my point.
Yeah.
What would be the motivation for the countries to do
because you can't keep adding and I mean, I think one can never underestimate the stupidity of government. So
yes.
Overestimate it. So yeah. Anyway.
Okay, so maybe we should move to different topic.
Sure, that's fine.
Yeah. So to cosmology.
Okay, I kind of figured we were going to head there.
Yeah, I brought 2 books. So yesterday I mentioned the vacuum dispersion effect. Yeah, you seem skeptical about vacuum dispersion being observable effect. So can you just elaborate a little?
Well, I mean, it is an interesting idea that at very small scales, which can only be probed by very high energies, that the nature of space-time might be slightly different in quantum gravity. And the highest energy cosmic rays are approaching the kind of energies where that might be observable. Mm-hmm. I just haven't seen any convincing arguments. It's more hopeful than suggestive. I guess the point is, look for it. But I guess in my having been around for a long time, I'm skeptical, and generally, most ideas are wrong.
Mm-hmm. That is completely true in science. It's
if they weren't,
99% at least.
If they weren't, anyone could do it, right? And so this is very hopeful, and most hopeful things are just that. So I guess that's my kind of skepticism more. I haven't seen any. If I saw that there was a convincing first principled argument that this is an effect that must be observable, then I'd be less skeptical. It's the same thing about something that I've spent a lot of time on, which is gravitational waves from the early universe, from something called inflation. It'd be profoundly important to observe them, and I spent a lot of time arguing where you might observe them and what their effects might be. And in fact, my colleague Frank Golchek and I showed, I think, remarkably, that if you could measure gravitational waves from inflation, you could prove that gravity is a quantum theory empirically. Mm-hmm. It's a really neat, very simple argument.
Can you repeat the simpler argument for this?
Yeah. But let me, before I repeat the argument, sure. But at the same time, there's no compelling argument that they should be visible. That I mean, the scale at where gravitational waves would be actually observable is a very specific scale associated with this period in the early universe called inflation. And if it changed by a factor of 2 or 4, they'd be unobservable. So while it would be very important, we'd have to be very lucky if they're observable. And for a while, it looked like we were lucky. There was a small period when they thought they observed them. There was a paper that came out, and it looked like it was an effect, and it was very important. Anyway, the reason that you can show this in a way that I could explain is that, well, what we used was something called dimensional analysis, actually, in the end. We did a detailed calculation, but and physicists use dimensional analysis because in the universe, there are certain quantities that describe how the universe works, and they have dimensions like space and time and mass. Basically, they're the major dimensions, and almost every physical quantity can be described in terms of space, time, and mass. Okay, and when we looked at the production of gravitational waves, we looked for its dependence on a key quantity called the Planck's constant, which tells you that if the Planck's constant went to 0, quantum mechanical effects would go to 0. The fact that it's non-zero represents the fact that quantum mechanics exists and changes the predictions of the universe compared to classical mechanics. And we showed just by dimensional analysis that that if you wanted to calculate the density of gravitational waves from inflation, that in fact the only combination, even without knowing how to do it, the only combination of space, time, and mass and Planck's constant would be such that it would depend on a positive power of Planck's constant. And therefore, if you measured it, it would show that it was quantum mechanical, because if Planck's constant went to 0, then it turned off. So it was really kind of simple to show that it was inherently a quantum mechanical process, which the equations, the calculations are done using quantum mechanics, but that doesn't prove it's quantum mechanical. Namely, I could calculate how a baseball thrown in from my hand gets to a pitcher. I could calculate it using quantum mechanical wave functions, all that. But in the end, I'd end up with Newton's laws. I'd end up with classical result. So the fact that I can use quantum mechanics to calculate something is not surprising, because after all, quantum mechanics describes the universe. But certain results are classical and don't need quantum mechanics to do them, and in fact would be exactly the same even if the world wasn't quantum mechanical, like a pitcher throwing a baseball. But in this case, we showed it would vanish. And so it would be really remarkable.
Are you hopeful for the LISA observatory in this regard? Because it should be sensitive exactly to this part of spectrum.
Yeah, but I think there's, of course I'm hopeful. I love, anytime we open a new window on the universe, we tend to be surprised. LISA itself probably won't be sensitive enough. You'd need a super LISA. Already, LISA is probably still a few orders of magnitude away from that. There are other ways to do it by looking at something called the cosmic microwave background radiation and its properties, which is how people thought they discovered it in the first place. Something called the polarization of that, and those experiments are getting more sensitive, but they're the ones that In order to see it has to be very special value. Otherwise, I think we have to wait not for Lisa, but Super Lisa, or maybe Super Lisa. And that's going to be quite a while.
Yeah, but if Lisa sees nothing, will there be, motivation to build Super Lisa, or it will see
I doubt it'll
supermassive black hole mergers?
And it'll see something. That's the point. It's going to see something. And it's not like, say, particle accelerators, where the Large Hadron Collider discovered the Higgs particle, but it hasn't discovered anything else. And as I've told physicists, even before, I said the worst possible thing could happen is the discovery of the Higgs and nothing else, because then we know there are problems and mysteries in the standard model of particle physics, but I don't think we can go up to politicians and say, guess what? We haven't seen anything. Give us more money. Yeah. And so
I think they are trying to do that.
Yeah, but it's hard. It's hard.
Yeah.
And I mean, seeing nothing is sometimes very important in science. It really tells you that something. And there's some famous experiments, the Michelson-Morley experiment, the fact that you couldn't see evidence that the Earth was moving through some background ether was a demonstration of Einstein's theory of relativity working. So null experiments, as they're called in physics, can be very important. But I remember actually talking to a young faculty member when I was chairman of a department who was applying for a job, and they had been looking for a certain kind of dark matter and hadn't seen anything and ruled out a whole range. But for many physicists who weren't in that field, having an experimental result that doesn't give any positive thing didn't make him optimistic that he'd get tenure. Put that way. Yeah.
You wrote a book about the universe coming to existence from nothing.
Yeah.
It was like 12 years ago.
Really? That far?
Yeah. Sorry, I didn't want
Yeah, it's all right. Time flies.
Yeah, time
Feels
flies.
like yesterday.
It does.
Has your claim aged well during those 12 years?
I think so. I think it's aged beautifully because it was correct. No, I don't think there's anything that's changed in any deep way about the arguments I made. And because...
Can you summarize those
arguments? And I mean, if anything, I was hoping for, more experimental data on certain things, but that hasn't happened. But it was a plausibility argument, which really ultimately needs a real theory of quantum gravity to be proved. But the argument is really quite simple. First of all, if gravity is a quantum theory, the variables of gravity are space and time. Einstein showed us that space-time, the curvature of space-time reflects the gravitational field and vice versa. So gravity is described as by the properties of space and time. And if gravity is a quantum theory, then those variables become quantum variables. Space and time are quantum mechanical. In fact, as we were talking about earlier, some people hope that fact would allow you to see what you said was a dispersion in very high energy cosmic rays. But in any case, so space and time are the fundamental variables of gravity. If they're quantum mechanical, then they behave quantum mechanically. That means they fluctuate. And space-times can pop into existence and out of existence, just like particles, elementary particles, pop in and out of existence all the time. We know that. These things called virtual particles, even though you can't measure them directly, we can measure their effects on the properties of atoms. And they allow us to calculate quantities to 13 decimal places. We get the right answer. We'd get the wrong answer if you didn't include the effects of these so-called virtual particles that are popping in and out of existence. So if space-time is quantum mechanical, then space-times can pop in, and the whole universes can pop into existence out of nothing, literally, namely no space, no time. Now, we know that virtual particles are virtual because when two particles pop into existence, a particle and an antiparticle, they violate energy conservation if they have mass, right? Because first you have nothing there and suddenly you have particles with mass. But the Heisenberg uncertainty principle of quantum mechanics gives you a little loophole. It says you can't measure things exactly. If you have only a certain amount of time, you can only measure energy with a certain accuracy. And so if these particles that kind of slip in there, if they exist for a time shorter, then you can measure that violation in energy conservation that would be due to their existence. Then they're allowed. It's, as I like to say, it's like politics and business. If no one can measure it, then anything goes. and it's that way with that.
Okay.
It's that way with elementary particles. So they can exist for a very short time. But particles that that say carry no energy could pop into existence, and they could exist for arbitrarily long times, and that happens in nature. Okay, so if you had a universe that say had zero total energy, it could pop into existence and not have to disappear. And there's strong suggestions that our universe has zero total energy, first of all. But most universes virtual universes, if you want, will disappear in a very short time. You could ask, what would the properties of a universe be that would pop into existence by the laws of quantum mechanics and last, 13.8 billion years, okay, without disappearing? And it turns out if you look at it, it would have exactly the properties of the universe that we see today, essentially. Now, that's highly suggestive, but it's not proof. Mm-hmm. It just says, well, a universe that did do just that could look like our universe. And if we see our universe looking like that, it's suggestive that that happened. And it shows you that without any supernatural shenanigans, you can create a universe, or no, not create, that's not the good word. A universe can spontaneously arise.
Be careful about
it. Yeah, exactly.
Creation.
Yeah. But exactly. Because English fails you, language fails you all the time. But so a universe can come into existence from nothing, and by that, and I talk about the nature of nothing a lot in the book, and people get hung up, especially philosophers and theologians get hung up a lot on this idea of nothing. Mm. But what I mean for the most part here is no space, no time, namely everything we see, no space, no time, no particles, everything that exists in our universe now did not exist. Now, whether anything else exists is a different question, but our universe didn't exist, and then it suddenly existed. And
so something different could exist, but not the space and time that we know from our universe.
And that's the and the other question is, it may be an interesting question for some people. It's not an interesting question for me. Well, in principle, it's an interesting question, but the really remarkable thing, the thing we should be amazed about, is that our whole universe containing 100 billion galaxies, each containing 100 billion stars, all of that could come from nothing. It seems to require something to, some creator. And the fact that it doesn't, it seems to me, is worth celebrating. And that's, I think, one of the reasons why my friend Richard Dawkins argued, and that at least in some sense, and one shouldn't put too much emphasis on this, that it proceeds to take what Darwin did for biology to the next step. Darwin showed that the complexity of life could arise simply by evolution and didn't require divine intervention. And a universe of nothing shows in principle how the complexity of our universe could arise from nothing without divine intervention. And so he put it on a similar framework. But it's not to suggest that a universe from nothing is the same as the origin of of Theses, which was a profoundly important book. Yeah.
So in string theory, or maybe in M theory, the picture is like you have a 10-dimensional something, and then 3 dimensions start just expanding. Is this the same picture? Like we had nothing before, but we are part of something different, and then spontaneously there was some phase transition.
I don't know if I don't think so. Well, yes and no, because I think in string theory and M theory, it's so vague as to say, it looks the same, but no, there's not mechanisms for which that happens. In fact, I'd have to say that one of the biggest failings of string theory, and I think Richard Feynman felt this way even when he was still alive in the 80s, is that it requires, in general, a universe with more than 4 dimensions. But it doesn't in any way explain why the universe we live in is 4-dimensional. He said that was one of its biggest failings. In fact, he argued that it makes excuses rather than predictions. And so, string theory in principle allows, although even now we understand the whole nature of dimensions itself is kind of a vague concept, but it requires generally more than 4 dimensions, and we don't observe them. I've never walked into an extra dimension that I know of.
Well, maybe you are just too large.
Yeah. And but in any case, but it doesn't explain why the 4 dimensions that we see are large and why other dimensions are small. There's no natural mechanism in the theory that suggests that, and it could just be an accident, and that's generally, unfortunately, the argument that's now given. Well, it's an accident. If it was any difference, we wouldn't be having this podcast right now. And that's potentially true, but it's not an explanation.
Well, maybe the universe doesn't owe us a good explanation.
No, it doesn't. It's not compelling. Mm-hmm. But it may be true. And the universe is the way it is, whether we like it or not. And that anthropic kind of argument, which we use a lot, including understanding the energy of nothing, which is one of the reasons I wrote that book, because nothing can have energy. Mm-hmm. It may be a vast cosmic...
Philosophers have to be really mad at you.
Well, I don't know. They get mad at me for a lot of things.
You had some issues.
But that just may be true that our universe is an accident and the fundamental properties of the universe are accidental. Mm. It's disappointing for someone like me who's old enough to have wanted to become a scientist, by wanting to explain why the universe had to be the way it is, and that's the way science used to work. And in the end, if we say, well, the fundamental reason is, argument is that it doesn't have to be the way it is, it's just an accident, that may be true. So we'll see.
And maybe we'll just find an argument for why 3 is the right number.
Yeah,
there's a new paper on arXiv every couple of months.
Yeah, and they're all wrong. But maybe one hopes that it would be nice if this really was a fundamental theory that was right, if it answered at least some fundamental questions about the universe. But right now, I have to say, while string theory has led to remarkably interesting mathematics and insights into certain physical theories that have been really useful, it hasn't, in my opinion, fundamentally explained anything about the universe that we see. Mm. Some people would say it's given some arguments about the nature of black holes and what's called the entropy of black holes, sort of, but it still hasn't answered the fundamental questions about the ultimate behavior of black holes. So I think it's fallen far short of what we hoped it would do. That doesn't mean it's wrong, and that doesn't mean it's not worth pursuing, but it hasn't explained the key things, such as why we live in a universe of 3 space dimensions, why the energy of empty space isn't zero, but it's very small and positive. Because in general, if you asked a thing theorist, if you locked them in a room and didn't give them any data, most of them don't care about data anyway. But if you didn't give them any data, they'd say, "Oh, well, the energy of empty space is negative," mm-hmm. and it isn't. So it's not got a good batting average in that regard. Mm-hmm. My friend Frank Wilczek has a good analogy that I like. He says string theory. What string theorists like to do is they like to throw darts on a wall. And then after the darts are there, they draw bullseyes around them.
So maybe just to finish this topic, you mentioned a person connecting black holes to string theory. Uh-huh. Recently on your Origins podcast, you had Leonard Susskind.
Yes, yeah.
And his description of our universe is completely different to what we are used to. His famous paper, The Universe as a Hologram.
Yeah.
Do you think we are, due to completely different perspective, are we waiting for next Einstein to completely reorganize physics?
Well, I think that quantum gravity will probably require some mm-hmm. great leaps, and it's going to be take a long time to do, if ever, because it's also hard to... Remember, Einstein was guided by observations. No matter what people think, he was ultimately guided by observations to lead to his and confirm his general theory of relativity. But the notion of the world as a hologram, of course, the mathematics behind that does come from string theory at some level, and there's seen as arguments about something called duality of it. But so I suspect that the ultimate description of nature will be more strange than anything we can imagine, because mm-hmm. the universe is stranger. So far, the imagination of the universe exceeds the imagination of human beings. So, and it would be amazing, by the way, even though it's extremely well motivated, and I know Lenny strongly thinks that string theory is probably correct, and has worked on it for a long time, and it's really well motivated by what we understand. But I still kind of think it would be amazing if it were actually true, because most physical ideas are wrong. But I felt that way, to be fair, about the Higgs mechanism, about the Higgs particle. I thought for sure the Higgs particle didn't exist because it just seemed too simple a way to solve the problems of the standard model, and I was
don't
sure.
like the simple solutions.
Well, it was kind of slimy. It was just sort of okay. You put it all in, create a new particle, and it solves all these problems. And I thought, well, probably reality is much more complicated, but it looks like that at some level. And I was very surprised that the Higgs existed. So, it could be that this the stab in the dark, well-motivated stab in the dark is right, but we just have to realize that most stabs in the dark in physics don't work.
So we shall see about that.
Yeah, and that's great. That's what's wonderful. Not knowing, as I said in my most recent book, which is called The Known Unknowns, at least in England, and since you get the English books here rather than the American ones.
Sometimes.
And it's about what we know we don't know about the universe. Which is really fascinating and not knowing is really at the heart of science because it's an invitation to discover. So I wish more people would be more parents and more teachers and more politicians would be willing to say, I don't know, because that's exciting. That's not embarrassing. That's exciting because it means there's something to learn. And so we'll see is a wonderful thing. It's an invitation to young people to say there's a lot left to learn. And I remember when I was a young person, it was a book by Richard Feynman that motivated me. It was called The Character of Physical Law, that made me realize that it wasn't all understood, that there was a lot left to learn. And I think that we have to, that's the kind of thing that can excite young people to realize that there is sort of job security in science because there's a lot we don't. And I expect it's not going to end. Even if we had a so-called, as they used to say, theory of everything, which is not really a theory of everything. It's a theory of very little. String theory is really a theory that would, if we had it, a theory of quantum gravity, it would help us understand the origins of the Big Bang and the ultimate fate of black holes. But other than that, it wouldn't be particularly, it wouldn't enhance our understanding of anything else in the world. It just gives some fundamental descriptions, but there's still a lot of things that need to be understood. That how oatmeal boils, how quantum properties of matter, and so there's a lot left to learn about the universe, and it's not as if it's going to that process is going to end soon.
You are very active in your science outreach programs throughout the podcast or throughout your books. Last book about climate change you wrote in 10 weeks, but there are people that make 10 seconds or 30 seconds videos on TikTok or other social platforms, and their outreach is, no offense to you, but
bigger,
much bigger than yours. Is it frustrating, or do you see scientists reaching to the laymen throughout the social platforms?
Well, I think, it depends on the day, doesn't it? Look, I don't think one can choose to be frustrated by the fact that certain things are popular, but it's always been that way. There's nothing new about that that certain things are always popular, and
it's fun to hate popular things.
So that's all right. But I think you can use it. And I've tried to do that. I've tried to use the popular culture as a way to get people interested in science. My book, The Physics of Star Trek, for example, was hugely popular because I used Star Trek, which was a cultural phenomenon in science fiction, and people could appreciate that who didn't appreciate science. So I think rather than being frustrated, we should try and use what the public is interested in as a hook to help them get interested in the real universe. And that's partly what I've tried to do in everything I've done, including the podcast, which is to connect science and culture. It's not just scientists I talk to; it's writers and actors and directors and journalists and artists and musicians, as well as scientists, because it's all part of a whole. The wonder of human culture and the ideas that are driving our sense of self in the 21st century.
But it's also like, okay, social networks are giving new tools to science communicators, but it's also forming the expectations of the audience and shortening the attention span.
It is.
Is this a good era for writing books?
No, it's true. People, if it's longer than a tweet, a lot of kids don't want to read it.
Yeah, exactly.
And that's a problem. And it's interesting because when I've been writing books for a long time. And I think I wrote my first book maybe over 30 years ago. And it was fascinating to see how I've had a few very big selling books, okay? And say The Physics of Star Trek, which I think came out in 95 or something, I forget, something like that, 93, 94, 95. And then The Universe of Nothing, both of which were big New York Times bestsellers, let's say. But the number of books that it takes to become a New York Times bestseller has dropped by a factor of 2. In that interim, because people don't buy books anymore, people don't read them, and we can bemoan that fact, but things change, and so it's a challenge to us to find new ways to reach people. I think it's sad, of course, as someone who likes reading, that young people don't like to read as much. But, the world changes, and you can spend all your time complaining about it, or you can move along with it. Or you can try and find ways to be interesting enough or attractive enough to try and get people to pick up a book. And I guess I'd rather try that than just give up.
Malcolm Gladwell recommends that dropping small rewards as a writer. Every couple of pages, some piece of trivia that people can just, show off to their friends. So do you think about this when you're writing? Like you are writing to a different readers as 20 years ago?
Well, yes, to some extent. But I guess I've been guided by the same principles when writing as well as lecturing, which is to try and recognize that people have a limited attention span in listening or reading, and so that concepts can't be too long. And also, you need to give people a break in between them with something relaxing. And also, when I write, I try and make it not consequential, so that if there's something you don't understand, it doesn't affect the whole rest of the book. Which allows me, because I do believe strongly in not dumbing down everything. I think people do want to be challenged sometimes. At least there's certain readers that do. And in every one of my books, I try and throw things in to challenge certain readers. But at the same time, hopefully, those readers who really find that part difficult can skip it and not lose track of the rest of the book. So it's a combination of things.
When I started writing, I hated personal stories because everything you read about gravity has to mention Einstein somehow. And I thought this is a cheating. But as I started writing books, I realized, this is a good, to cool down the pace and just, write one page about life of Newton or something like that. And
people like personal things.
Exactly.
And I also am fascinated by history anyway, and I often find it useful. And it's also fun for me. The point is that people don't realize that everything I do is for me, ultimately. But I don't think that makes me special. So I write books, obviously, with a reason, but I write books for myself in some sense. And so for me, a book is a voyage of discovery. If it's just a regurgitation, it's not interesting. And so I learn things in every book I write. I pick a subject sometimes which I may, I have some basic ideas about, but which are going to require a lot of learning. And that's why if you don't do that, you tend to write the same book over and over again. And I know a number of people who do that, and I won't mention names. But
Please don't.
But giving myself that challenge means that the books are different. But it also means that it's interesting for me. And part of it is history. Learning the history is fascinating. Like in the climate change, I didn't know about the history. And some of it's just fascinating. And
when you write your first sentence, what percentage of the book is already in your head, and what is to be discovered?
It's a good question. First of all, the books usually take me in directions I didn't expect. I used to say it takes me about half the time of, if I look at the full time of writing a book, the first chapter is half the time. And the rest of the book is the other half.
First chapter is
because I've got to find, and I try a lot of different things, and I don't know where I'm going. And by the time I finish the first chapter, I have a sense of where it's going. But then sometimes it takes me in directions I never expected. And so, as when I do an audiobook, when you record an audiobook, I often redo the first chapter at the end because your pace of your talking changes in the way, and the first chapter may sound different than the rest of the book. But the same thing happens with my book. Sometimes I'll go back and reflect on what's actually there and make some changes at the begining.
Do you rewrite a lot? Because I hate it.
Yeah, I know. Well, everyone hates it. Everyone hates it. I try to do it at a minimum. There have been only a few occasions where I've had to drastically rewrite a book. My book on Feynman, which is one of my favorite books, a book called Quantum Man, which is a scientific biography of Richard Feynman, the first real popular scientific biography. There were books about his life and all of that, but I wanted to talk about why. Sure, he was an interesting character, but that's not a reason to understand. I wanted to talk about why he mattered as a scientist. And I was asked to write that book, and I never wrote a proposal, and I was just honored to do it, mostly because I thought this will force me to read all of his papers, which otherwise I wouldn't have the discipline to do. And when I wrote that book, I wrote it, and the publisher who asked me to write it, when I sent him a first draft of the first half of it, which, by the way, I usually don't do with publishers, but I did in this case, came back and said, what's all this science? And then I realized I rewrote it, but I didn't have to rewrite it significantly in a sense, because what I did was I worked his life biography into it in a way that all the science was still there, but it wasn't obviously as noticeable, because I sent it back to him with this, weaving these personal stories in the midst. And he said, "Oh, great, this is what we wanted." But all the stuff that was originally there was there. That was probably the most drastic version of rewriting. But no, I don't rewrite a lot. By the time I get to the writing stage, I kind of know where I'm heading. Yeah.
So maybe to move to a different form of art, there is a movie you told me about yesterday, The Unbelievers.
Oh, yeah.
That describes you and Richard Dawkins as sort of a rock stars touring with scientific content.
Yeah.
And this year I was at 6 different festivals with science talks and discussions and so on. But I noticed there is a difference between how music makes people feel and how even a good talk make people feel. So is there a huge difference? Are we tickling different part of the audience brains, or?
Well, it depends how you're talking. I think the aha experience is orgasmic. I think museums, I used to work in a science museum when I was a kid, which, by the way, impacted on obviously on the way I try and explain things. It was a very useful learning experience, an unbelievably useful learning experience. But the museums talk about this aha experience. Everyone has it when there's something that they understand, something basic that they understand for the first time that they never really realized they understand. That aha experience is seductive and pleasurable. And I don't think it's that different than great art or music, the feeling that you get from it. The difference is that I think music, more than art, but music, let's talk about that in particular, reaches people more easily. We have an innate evolutionary appreciation for music, even if we can't do it. And you don't have to know anything about music to either appreciate a Bach cantata or Eric Clapton playing the guitar, okay? And the difference with science is that there's a higher threshold that you need to get to before you can appreciate it. So that is definitely true. And so it's easier for music to reach people, more people more broadly than it is science, and that's just the way it is. But I think people can have the same sense of the kumbaya experience. You say, I mean, in a music concert, everyone's together and everyone's smiling and a lot of people are stoned, which is a different thing. But anyway, but I think you can in certain events that I've spoken at in these big venues, that you get that same sense of community, like-mindedness, people there for a common purpose and enjoying each other. I think one of the reason people go to church every Sunday is for that experience of community. So I think we could, have quantum mechanics classes every Sunday and have everyone together. Maybe not quantum mechanics classes, but we certainly be. To be more serious, people have said, well, religion gives us something that science doesn't, and I think that we can ask, what does religion give us? And then ask, how can we reproduce it, but with descriptions that actually describe the world instead of fairy tales?
So it's a different experience, but it can be a deeper one, actually, probably, because I can probably quote some pieces of music that had some impact on my life, but maybe some quotes of Richard Dawkins, we are all going to die, and that makes us the lucky ones.
Yeah.
It's deeper than probably any music.
Well, yes, no, but that may be myopic for you to say that, in the sense that I suspect some people who have an incredible appreciation for music have that experience when they hear a piece of music, Mozart, say, or a Bach. I mean, the many voices and all of the rest that I can't get. And so they may have a very deep, almost mystical experience that we don't have. And I think we have as scientists, we are able to appreciate certain aspects of science that other people can't. We can try and relate it, but you can't reproduce it. But I think it's also true that music impacts on us in a different cerebral way than language, and we don't. again, it depends if you're musically oriented. Most of us don't reflect on the music as much as experience it. Whereas when it comes to scientific discussions or the written word, we reflect on it much more, and therefore it can have a deeper and longer lasting effect. An amazing quote can have a more lasting effect for most of us, although for some people, I suspect a musical phrase can have a deep and lasting effect. You know, I often wish I was one of those people who could get as much. I love music, but I'm not. I play a number of instruments very badly, even though, as I like to say sometimes, and I don't usually publicly, I've been nominated for a Grammy, and I've soloed with the Cleveland Orchestra, and I wrote the libretto for a symphony, but I don't have any musical ability.
It doesn't sound like it.
I know, it sounds good. It sounds good on a piece of
paper. On paper, it sounds
good,
perfect.
Yeah.
Well, Rick Rubin says, no, he can play no instruments and cannot produce music on his own, but he's just very good taste and confidence in his.
Well, there you go. Yeah. Well, I wish I could. My daughter was very musical, and I wish I could sing. I wish I could play instruments. I love it, and it's very frustrating in a way. But it's nice that I can appreciate it. At least that. Whereas, you know, some people say they can't do math. I think mostly they don't want to spend the time doing it. I realize there's different abilities, but I think most people can do math without if they work on it. We just don't demand it. But I think the difference is that I can appreciate music without having those abilities, and for many people, you can't appreciate the math without at least a little more work.
And there's this book, Gödel, Escher, that one can maybe use to argue that at the deepest level, those completely different things as art, mathematics, and so on are somewhat connected.
Oh, sure, that was a very good selling book, and my first publisher was the same publisher who published that book, and we had long discussions about it. But yeah, I mean, there's no doubt there are very deep mathematical connections in some ways between music and that. But again, experientially, the way people experience mathematics and music is undeniably different.
I think.
Yeah.
Most people would agree with this statement.
Yeah.
Do you think that science now is a polarization factor now in our society?
Well, everything is a polarization factor now in our society, and it's unfortunate. And I think part of it is just the social fabric is being changed. Part of it, I think, is an unfortunate, is due to scientists. I think with the COVID pandemic was, for me, an opportunity to explain how science works. One of the things I having written about Star Trek, that I say that it's unfortunate about Star Trek is every time there's a big problem in Star Trek, they solve it in 2 hours. They come up with a scientific solution. You know, it takes 45 minutes to figure. In the real world, it doesn't. It takes years and decades and decades. And when COVID hit, I think people had this expectation, we'll be able to understand it and cure it in a week, right? And instead, it was an opportunity to say, look, we don't understand anything about it. Here's how science works. Some scientists are going to put forward a hypothesis. It's going to be wrong. It's going to be tested by other scientists. And we'll slowly learn more about it. And it's actually amazing that within a year or so, we had a vaccine. Yeah. That is unbelievable. But instead, you had all these people including some scientists, some doctors, making these pronouncements about, this is what the science said, when we didn't know, because you can't know, because it hasn't existed before. There aren't any cases. You don't know how the human body is going to respond. And it would have been a great chance to say, look, we don't know, but we're going to try this, and it might not work. And we're going to try this. And maybe because we don't know how it works, for safety's sake, we should try this, but not, hey, you have to do this because we know it's going to work. And masks are an example. For safety's sake, because we don't know, let's use masks. And then here's how vaccines work, and here's how they don't work, and here's how we test them. And it was a great chance to show at the cutting edge how uncertain science really is. But some scientists and other people and politicians are scared by the notion of uncertainty. They have to appear to be certain of the things, and that's really, I think, did a disservice, because, of course, when people are certain about things and they're wrong, people distrust things. And on the whole, that characteristic of being certain about things and being wrong is the generic property of politicians, not of scientists. But when scientists have joined that and been claimed to be certain about certain things and been wrong, public confidence in science decreases. So I think it was a learning opportunity that was unfortunately blown, in my opinion.
And regarding the polarization, I feel that people are not capable of maybe disagreeing respectfully, because there are long conversations you probably had with Jordan Peterson, Sam Harris did as well. There was a strong disagreement, but expressed with respect. Then short clips came from that on social networks, and taken out of context, it seemed like nearly aggressive. So how in this era should we be learning how to be respectfully disagreeing with someone, but still being, capable of reaching large audiences?
I think one of the few ways is humor. If we can laugh,
sure,
and make fun of ourselves, that helps. So I think injecting humor into human relations often diffuses otherwise aggressiveness. But it's hard to. I wish I had a magic bullet to solve that problem, because sound bites will always distort things, and disagreements don't sell, right? If you're looking for clickbaits, having people say, "Oh, I agree with what you say," it's not going to get people.
That's a nice point.
And so
that will never be viral.
So people are always looking for some ways to get people to click on something, and disagreement sells, and like sex. And so it's you just got to understand that that's the way the world is, and try and work on that. But I did. As you know, I did say a Ricky Gervais and I've done a podcast, and I think
I love him.
That was an example of how one can use humor to try, and even when you disagree. Anyway.
So yesterday when we spoke, and today during this podcast, you mentioned many interesting people. So who can you recommend someone to pay attention to? Like you had your good friend Stephen Fry, or?
Well, there are a lot. Look, people. There are lots of interesting people in the world, and so. Pay attention to all the people that I talk to.
Okay.
But I think I'm always, for me, it's always a pleasure to discover new people that I didn't expect, and you know what? At some level, everyone has interesting stories to tell or interesting comments to have. But there are remarkable people, and I think for me, as one of the biggest surprises as an academic who sort of revered academia for most of my life when I was growing up, and obviously was involved in it for many years, I used to somehow think that the most interesting, brilliant people were academics, and it was really a great discovery to find out that wasn't true.
Yeah. So. In what way? Like the academics were worse, or non-academics were better?
No, I think non-academics are, the point is that academia is a very safe environment. And even though, at some level, creative thinking is important, you can survive there's great safety in not veering far from the path if you're an academic.
Okay.
But in other areas of human activity, you've got no safety net, and I'm very impressed with people who can make achievements in that environment. So I've discovered, and people who have no classical education, and they're remarkable, and so that's great. I love that.
Is it like because academics don't have the skin in the game sometimes?
Yeah, I think it's a combination of that, and their academics are often talented in one thing, and academia is an environment where they can utilize those talents in a very, very safe way with a lot of support. And that's great, because that kind of safety net does allow incremental progress. Most academics are not, groundbreakers, right? It's not that way. I mean, academia, and generally science proceeds in baby steps. The media make it sound like there's a revolution every 2 minutes, and there's a new Einstein every 3 hours.
The big leap and so on.
Yeah, and it's not. And although I've always amused when people say a quantum leap, because the quantum leap is actually pretty small. but anyway, that environment works, but it doesn't encourage necessarily innovators. Innovators can survive and flourish in that environment too, if they want, but doesn't necessarily encourage that. Mm-hmm. And I think academics also, it allows people who are timid to function, and most academics generally, and this is part of the problem of academia right now, and I've been writing about it, it's that academics don't want to speak out because most academics just want to live below the radar. They just want to work on their stuff. They don't want their department chairs or deans to find out what they're doing or ask
understand what they're doing,
or ask them to do something else and be on a committee or when. And so speaking out against the kind of threats to free speech and open inquiry is something most academics don't want to do because they get noticed if they do it. And also speaking to the public is something many academics don't want to do because it is scary. Yeah. It's suddenly you're open in an environment that you're not used to. And so, academia has its functions, but it's not, academics are not necessarily, courageous, let me put it that way.
Lawrence, thank you very much for having time to sit with us and talk with us. We are at the end of our time. Maybe someday when we will return to Slovakia, we can have a second edition of this podcast. Do you have some parting words for our listeners that you want to convey to them?
Well, first of all, thank you. I really enjoyed it. The quality of the discussion was really great, and I would love to return
Thank you very much.
And I guess, your listeners, I'd just say don't believe everything you hear.
Even on this podcast.
That was implicit, but yeah, that was right.
Okay, so thank you very much again. Okay. Have a nice day. Okay. My vám veľmi pekne ďakujeme, že ste počúvali toto špeciálne vydanie nášho podcastu s profesorom Lawrenceom Kraussom, kde sme sa rozprávali od jeho kníh cez environment až po vedu. Takže majte sa veľmi pekne, nájdete nás na všetkých dobrých a troška horších podcastových aplikáciách a máme aj stránku vedator.space a aj aplikáciu Vedátorský. Majte sa veľmi pekne.
Majte sa.
Volám sa Zuzana Kovačič-Hanzelová a v živote som mala šťastie. Narodila som sa do podmienok, v ktorých je všetko nastavené na úspech. Aj preto som pre vás pripravila spolu s Kristínou Paholík-Hamárovou minisériu Odsúdený na neúspech o téme generačnej chudoby, vylúčených komunít a systéme, vďaka ktorému sú 100 000 ľudí odsúdení na neúspech. Nájdete nás na Sme.sk aj vo všetkých podcastových aplikáciách.